Hi guys, so in this video we're going to be covering real-world exponential growth and decay. So first let's talk about what is an exponential function. Exponential functions are functions that the variable is in the exponent. So for example, on the right here, we have a function f of x equals x squared. Now notice we do have an exponent, but that exponent is a constant value. It's a fixed 2. This is actually a polynomial function, right? It's degree of 2, so it's a quadratic function. This is not an exponential function. Looking over here in purple, we have f of x equals 2 to the power of x. Notice here, the variable is in the exponent. This exponent is not a fixed value. It is x, which is our variable. So if the exponent has a variable, that is an exponential function. Okay? Now, we have two different types of exponential functions that we're going to be looking at today, growth and decay. All right? Now, exponential growth and decay, you know whether it's growth or decay based on the base of the exponent. So whatever this base value is will tell you whether it is growth or decay. If b is positive, if it's bigger than 1, then the exponential function is actually growth. So if the base is bigger than 1, it is growth. If b is less than 1, bigger than 0, then you have exponential decay. Right? Now, this is the general look of exponential growth. You start off kind of slow and then you quickly speed up. Exponential decay is the reverse. You quickly lose and then eventually kind of gets less steep with your decrease. Now, just like the name suggests, exponential growth is going up and increasing. Exponential decay is going down and decreasing. Okay. Another thing that we need to talk about is the restrictions that we have on the base, okay? The base has to be positive. It has to be bigger than 0. No negative bases. Another issue is that the base cannot be 0 or 1, okay? The reason why it can't be 0 is because if the base is 0, then you would just get a horizontal line, right? 0 to the power of anything is just 0. So you will get a horizontal line on 0, which would be the x-axis. And the same thing for 1. 1 to the power of anything is 1. So you would just get a horizontal line at 1. So it's 1 higher than 0. 1 unit higher than the x-axis. Okay, so just some quick, because I really don't think it's going to be difficult for you to tell the difference between growth and decay. Here's some quick look at it. So we have 2.5 as the base. That's obviously bigger than 1, so that is growth. 1.1 as the base. That is also bigger than 1, so that is growth as well. 0.8 is smaller than 1, so that is decay. All right. Now, let's talk about creating these exponential functions. And the exponential growth and decay is really for real-world problems, okay? There are other types of exponential functions that we could graph that are not, of use, very common in real world. So today we're just talking about growth and decay. So when you're creating these exponential functions today, and just the general format of exponential functions, you have some value a, which is a number. It's a constant, which will be your y-intercept, your initial value, multiplied by b, and b is your growth or decay factor, to the power of t. Now, t is a variable. So a will be a constant number, fixed number, y-intercept, and b will be a constant number, fixed number, your growth or decay factor. Now, how do you find that growth or decay factor if you have a rate? So if I tell you that it's going up, it's tripling every hour, then your growth factor would just be 3. It's growth because tripling would mean that you are increasing, right? The number is getting bigger. So that would be a growth factor of just 3. So in the base here, it would be 3. But what if instead of giving you the factor, they give you the rate that it's going up by? Well, if you're given the rate, then you would add or subtract that to 1, depending on if it's growth or decay. So if it is growth, then you would add to 1. If it is decay, you would subtract from 1. So R would be your rate, whatever that is, and you have to put it in decimal form. Usually when they give you a rate, they give it to you like a percentage. So if I tell you that, your money is going to grow at a 4% rate, then that would be, that would be the percentage form of it. You would have to write it for the equation in the decimal form, which 4% would be 0.04. To change a percentage to a decimal, you move it 2 decimal points to the left, okay? And you would do the reverse. If you have a decimal and you want to change it to a percentage, you would move that 2 decimal points to the right. So 0.25 would be 25%. All right, now let's talk about the variables, right? What is the input and what is the output? The input, T, is usually time, but specifically, time is not always the same. Like if I tell you it's over 8 years, but you're gaining this interest biannually, 2 times a year, then it's not really being counted. The rate is not being counted just 8 times for the 8 years. You're counting it 2 times each year, so you're counting it a total of 16 times. So T will be the number of increases or decreases. Decreases obviously if it's decay, increases if it's growth. And then A of T, your output, is whatever the amount is that you have. That amount could be money, it could be population, it could be bacteria, it could be anything. A lot of different real world problems are actually modeled by exponential growth or decay. Now, the amount obviously at time T, whatever, the time is, whatever the amount of time, but the amount that you have in there. So the output is how much, and the input is how many times that it was counted. All right, one last thing that we need to cover, and then we'll get into an example. This last thing I want to cover with you, because it is a very common misconception, okay, that we have. Rate versus the factor, okay? The growth decay factor is the number by which the quantity multiplies. The growth or decay rate is the addend by which the quantity increases or decreases if it's decay. So let's put this in an example. Let's say you're gaining compound interest in your account, and compound interest is a growth situation. It's an exponential growth situation. If your investment is giving you 12% annually, that means that each year your total is really multiplied by 112%. Why? Why isn't it just 12%? Well, because you're not losing the 100% that you still had in there. You're not losing that money that you put. So you're just gaining 12% on top of what you already had in there, which in the account, which is 100%. So in this scenario, right, the growth rate is the 12%, while the factor is 1.12. Usually the factor is a decimal and the rate is written as a percentage. Of course, the way that you write a number doesn't really matter. Like I could write a number as a fraction, or I could write it as a decimal, or I could write it as a percentage. It's different ways of representing the same number, but normally what we do is we represent rate with a percentage, and we would represent factor as a decimal. But the important thing is that the rate, the factor is actually calculated with the rate. So sometimes you might just be given the factor outright, Like it's quadrupling every 3 hours. Okay, well then the factor is 4. It's quadrupling, so you're multiplying it by 4. The factor is what you're actually multiplying by. The rate is only the percentage, which then you would add to 1 if it's growth or subtract from 1 if it is decay. So remember that the factor, if you are given the rate, is 1 plus or minus the rate. Whatever, if it's growth, plus if it's minus decay, or if it's decay minus. All right, so I won't continue any further, but just remember, rate is very different than factor. Factor would be the entire base. Okay, so this is the factor, calculating that 1 plus or minus r. That whole thing is the factor. The rate would just be r. All right, so hopefully we got that clear. Let's look at a problem. Okay, now we already talked about exponential functions, and the way that exponential functions are different from linear functions is that linear functions have a constant rate, right? You go up by the same amount every time. If I'm going 50 miles per hour for 5 hours, I'm going 50 miles per hour the first hour, 50 miles per hour the second hour, 50 miles per hour every single hour. With exponential growth or decay, the number that you increase by is not a constant value, okay? It is not added by a constant value. It is multiplied by a constant value. So you have a common ratio, not a common like added number or subtracted number. So the ratio will be multiplied in exponential growth decay, whereas in linear functions, you add or subtract the number. So let's take a look at this table, which is modeling exponential growth of a money in a bond fund. Now, I know that this is exponential growth because we could see the numbers going up, right? So if you're increasing, it's exponential growth. If the numbers were decreasing, it would be exponential decay. So here they're asking us, what is the starting amount of the money? Well, the starting amount is the initial amount. What did I have at year 0? At year 0, I had $1,500, $1,500. The next question is asking us, what is the ratio or the rate that the money, the amount of the fund is increasing by? Now, there's a very simple equation to find this, and it's right here, okay? The first change divided by whatever the initial amount is. So the first change is just whatever the change is from the initial 0 year to that first year. So that's a 93 change. So the first change would be 93, and then the initial amount is 1,500. So then I could just use my calculator and do 93 divided by 1,500, and we get 0.062. Now, you can leave this rate as a decimal like this, or you could write it as a decimal, as a percentage. Remember to change it to a percentage, move the decimal point twice to the right, so it'd be 6.2%, okay? So you could write it either way. You could write it as 0.062, or you could write it as 6.2%. What you cannot do is write it as 0.062%, or just write it as 6.2. All right, let's take a look at this example. Consider the following table that models exponential decay of a fish pond, of a fish population in Lake Placid. Now, I know that this is decay because look at the number of fish. We're dwindling, okay? So the first question is, what is the beginning population? Okay, well, the beginning population at year 0, we are at 14,204 fish. And then they ask us, what is the ratio that the population of fish decreased by? Okay, well, let's look at the first change. Let's do 13,494 minus 14,204 is negative 710. And the negative is just there because it's decay. When you say the rate, you won't say it with the negative because you don't need, like, you know it's decay, you know it's decreasing, so the negative we do not write. So 710 divided by 14,204 is, I'll round this to the nearest hundred, so 0.05. Okay, so we have 0.05. Okay, obviously, yes, it's negative, but when I write the ratio, I will write it as the decreasing ratio is 0.05. Or I could write it as a percent, 5%. Okay. Now, one thing that I do want to mention, because there are two types of things that you will be asked here. You'll be asked to write an exponential function, and you'll also sometimes be asked to evaluate for a certain value. So the exponential function equation itself is just what equation you could use to find the output amount at any time t. Whereas when you're evaluating, you're given a certain value. I want to know how much money after 8 years, right? Whereas when you're writing just the function, they usually just tell you, here's the rate, here's the initial amount, give me the function. They wouldn't give you something to find. So evaluate is when you're trying to find a specific amount, whereas writing an exponential function, you're just writing the rule based on the scenario, okay? So let's take a look at 1 and 2, okay? Number 1 says a certain prescription drug is eliminated from the body at a rate of 10% per half hour. How much of a 250 milligram dose is left after 4 hours? Okay. Now, first, let's go ahead and highlight all of our important things, right? Rate, and this is the initial amount that we have, 250 milligrams. Remember that for our exponential function, right, we have A times B to the power of t. A is the y-intercept, the initial amount, and B is whatever the factor is. It's the factor. If it is exponential growth and you're given rate, you would find that by adding 1 to r. And if it's exponential decay, you would do 1 minus r if you're given a rate, okay? If you're given the factor outright, then you just use the factor. But if you're given a rate, like a percentage like we are here, we're going to have to do the calculation for the factor. Now, let's go ahead and do that, right? Now, look at the question and notice that it says that the prescription drug is being eliminated from the body. So do you think that that's growth or decay? Well, it's eliminating. So you're losing that prescription drug from your body. So that will be a decay. So to find the factor, we're going to go ahead and do 1 minus the rate. The rate as a decimal would be 0.1. Okay, so the rate is 0.1. So I'm going to do 1 minus 0.1, which would be a factor of 0.9. Okay, so now we have everything we need because all we need to write the function rule is A and B, the initial amount and the factor. So this function, f of t, will be A, which is the initial amount of the prescription drug, which is 250, and then times the factor, which we found is 0.9, to the power of t. Now, whenever I write a function rule, I like to write what is the input represent and what is the output represent. Okay, so t represents the time per half hour, because this rate is given to you per half hour. So the times, each how many times total each half hour. So if you have 10 hours, then that would be 20 half hours. So how many half hours? And then f of t, the output, will be the amount of the prescription drug. Left. Okay. So let's go ahead and find the answer to the question, because the question didn't say write the function that can model this situation. They ask you how much of this amount is going to be left after 4 hours, okay? So the question is, what is the input? Is it 4? Well, remember that the rate is every half hour. So how many half hours are there in 4 hours? 8. So t is 8. So let's find f of 8. So we need to do 0.9 to the power of 8 and then multiply that by 250. Remember, you have to follow order of operations. So you do exponents first, and then you multiply the 250. Okay, so we get 107.6. Of course, this is a real world problem, so 107.6 what? The amount of the prescription left, right? Which is measured in milligrams. So we have 106.7 milligrams remaining. All right, let's take a look at number 2, and then I have a couple for you to try on your own. A culture of bacteria doubles every 10 minutes. If we start with a culture, so starting of 5 cells, how many will we have after an hour? Okay. So first, let's go ahead and write our equation, right? Now, this is the initial amount. So A will be 5. And the difference from this question and 1 is that in 1, they gave us a rate, and we had to calculate the factor. But in number 2, they give us the factor. You're doubling. So you're multiplying 2. That is the factor. So B is already given to us, and B is 2. So this function would be f of t equals a, which is 5, times b, which is 2, to the power of t. And again, let's just go ahead and write what the input and output represent in this scenario. Now, t, again, will be the number of times per 10 minutes. So how many of those 10 minutes have there been in the total time? And f of t will be the output, which is how many bacteria there is. So the amount of bacteria. Okay. So now what is t, right? Now remember, t will be how many times in the amount of time that they give you are there 10 minutes. So we have an hour. How many 10 minutes are there in an hour? Okay, well, there's 60 minutes in an hour, so that would mean a total of 6 10-minute increments. So t is 6, so we need to find f of 6. So we have 5 times 2 to the power of 6. Of course, again, exponents first, so you would do 2 to the power of 6 first. However, one thing that you could do with this calculator is input it all together. So 5 times 2 to the power of 6, and it will do the order correctly for you. So we get 320. So 320 what? That's the output, right? So 320 amount of bacteria, so we can say 320 cells of bacteria. All right. Now go ahead and pause this video now and try 3 and 4 on your own. All right, so let's take a look at number 3. The population of toads in an infested pond is decreasing at a rate of 4% per hour. How many toads will be left after 2 days if the starting population was 3,400? Okay, so this is our starting population, which would be A. Now we are decreasing, so this is R, right? The rate is 0.04 as a decimal. Since this is decreasing, the B will be 1 minus 0.04, which would be 0.96, okay? And I'm just going to verify that. I don't know why I'm questioning myself right now. 1 minus 0.04. Yeah, that's definitely 0.96. Anyway, all right. So now we can write the equation, right? F of t equals the initial amount that we had, 3,400, times my factor, my decay factor, 0.96 to the power of t. Again, input and output, what do they represent? T, now remember the rate is per hour. So T is going to be how many hours have been. I'm not really using very good English, but you get what I'm saying. So how many hours have passed? And then F of t, the output, is we're talking about population of toads. So this will be the amount of toads that we have. Population of toads. Okay. So in this question, they ask us how many toads are going to be left after 2 days, okay? So in 2 days' time, how many hours have passed? Well, there are 24 hours in a day, and there's 2 days total, so we've passed through 48 hours. So T is 48. Okay, so 3,400 times 0.96 to the power of 48. So I'll just type that into my calculator. 3,400 times 0.96 to the power of 48 is, we're talking about number of toads. So I'm going to round that to whole toads. So after 2 days, there are 479 toads in that pond. Which is not a whole lot considering we started with 3,400. All right, let's take a look at number 4. Number 4 says a culture of bacteria triples every 15 minutes, okay? So triples, which means that B equals 3. We have the factor right away. If we start with a culture of 20 cells, so we're starting with that, so that's our initial amount, that's A. A is 20. How many do you have after 2 hours? So let's write the equation first. F of t equals the initial amount, 20, times our factor, which is 3 to the power of t. And t and f of t, what are the inputs and outputs? Now, this is the rate is every 15 minutes. So the input will be the increments of 15 minutes. So how many 15 minutes have passed in whatever time they give us. And then f of t is the output, which is how many bacteria we have. So another bacteria question. Okay, so in the question specifically, they ask us for how many do we have after 2 hours. So how many 15-minute increments are there in 1 hour? Well, there's 60 minutes total. So that means that there are 4 15-minute increments in 1 hour. So there are a total of 8 15-minute increments in 2 hours. So T is 8. So F of 8 equals 20 times 3 to the power of 8. Okay, and if you're doing this on another calculator that doesn't do operations for you correctly, remember, do the exponent first, 3 to the power of 8, and then multiplication after. So we have 131,220. Wow, 131,220 cells of bacteria. That's a lot. I guess if it's tripling every 15 minutes, that's a very quick rate, right? Your factor is quite large, so you're increasing by a lot. All right, guys, so that is it for today's video, and I'll catch you guys in part 2. Bye.